Okay, good morning everyone. It's time to start. So first our HD camera has already been fixed, so it's ready for use. And so if you want to watch the recorded video after the class, it will be much more clear. Because on Tuesday the camera was down, and I have to switch to an older one, which is not that clear. Okay, so let us continue with the decision trees. I finished wrap up the remaining little things. So in the last lecture, we actually have covered all the important details about decision tree learning. Okay? So like in ID3, the classical decision tree algorithm, we know it provides a general framework to create the tree from data. It essentially follows a greedy strategy. So ideally, we want our tree to be as small as possible. Why? Because we believe in the open readers principle, meaning that we want to select the model as small as possible, as simple as possible. However, to find a really globally small tree is infeasible in practice because you have to do a combinatorial search. Right? You have to enumerate all possible orders of the attributes used to split data and compare the tree size. Right? That's definitely feasible. So trade-off to the efficiency, we have to use some greedy heuristics. That's why ID3 is motivating. Right? So the strategy, the heuristic is that okay, at every step, I'm gonna select an attribute which seems best at the current step. That's why we call it local optimum. And then we partition the data set, and then we do the recursive procedure to partition each subset, and hierarchically until we reach the leaf node. Right? So then the question is, how do we decide a feature or an attribute is the best at the current step? Right? So the idea is that, okay, I want to use the attribute. After using that attribute to split on data set, the improvement of the purity, label purity, is the largest. Meaning that after using that attribute to split the data set, okay, I can say the purity of the labels are better than using all the other features. So the purity means that, okay, the more biased one attribute over the others, the better the purity, right? So if all the examples in one subset share the same label, then you have achieved the highest purity. Right? That's the idea. So if at each step I can find a best feature that could maximally increase the label purity on the splitted subsets, I expect that only after a few steps I'm gonna reach the leaf node. So you can imagine that you won't do many splitting procedures. You end up with tree leaves. That's why we believe in so doing we can find a quite small tree. But that's just a greedy heuristic. Right? If you know the greedy algorithm, in most cases actually greedy algorithm does not yield the result which is the same as some global search algorithm. Right? You cannot guarantee running ID3 algorithm will end up with the truly smallest tree among all possible trees. Right? But numerous practical experience have told us that doing so can end up with a pretty nice small tree which generalize well, but the speed is very fast. So that's the key idea. So now we need to decide, we need to measure the purity improvement, the label purity's improvement after using one attribute to split on the current data set. Right? So the very first measurement we introduced is the information gain. Right? So it is based upon the fundamental concept entropy. I believe most of you have heard of that. Entropy measures the uncertainty of of the labels in the current data set, right? So it's like two sides of one coin, right? The larger the uncertainty of the labels, the less purity, right? So if all the examples have the same label, you have zero uncertainty, and the purity achieves the maximum, right? So that means the larger the uncertainty, the smaller or the worse the purity, or the smaller the uncertainty, the larger the purity, right? So to measure the improvement of purity, we can just calculate the reduction of the entropy, right? You calculate the entropy before you use that attribute to split on the data set. And then after splitting, you calculate the entropy of each subset and then calculate their weighted average. Here, weight is proportional to the size of subset because we need to consider the importance according to the size of subset, right? And then their difference indicates the reduction of the uncertainty. The other hand reflects the increase of purity. Right? That's the key idea of the information gain. Right? But actually, we have other alternatives. It's not necessary to use entropy to reflect the uncertainty. Like we have introduced other measurement like majority gain, majority error, and the Gini index. Right? Majority error is kind of counterpart to uncertainty. Right? If you use the majority label to predict all the examples in the current data set, right? What is the error? So obviously, the larger the majority error, the worse the purity. Right? So the majority error can achieve 1/2, right? If you have two possible labels, right? And at that time, the purity is the worst. Right? Positive and negative examples are 1/2. And but if your majority error is 0, meaning that all the examples have the same label, right? That means that okay, you got a very good purity, right? They actually have achieved the best purity, right? So similar to the case of entropy, the larger the majority error, the worse the purity. Right? So you can also use the reduction of the majority error to indicate or measure the improvement of the purity. Right? So accordingly, you can follow the same. You can follow the same formula to compute the majority gain after using the attribute to split on the data set or Gini index gain. So that's why in our homework 1, once you have implemented your ID3 based on information gain, it is very easy to switch to other heuristics like Gini index and majority error. That is also required in the homework, and hopefully by running your different variants of ID3, you can compare the learned tree structure. They are not guaranteed to be the same. Okay, and then in the last lecture we talked about another important strategy in practice, that is how to deal with the missing attribute. Right? We talk about the most straightforward approach that you just complete missing attribute value with the most common value in the existing data, or a more elegant version, you use fractional counts. Right? You break this one complete example into 3 fractional examples, where fraction corresponds to the probability or the chance you believe your missing attribute take a particular value. Right? And then you just throw these fraction examples into the information gain computation or tree construction algorithm. You construct the tree, right? So the procedure is the same, but just don't feel uncomfortable. Right? The computation is exactly the same. There's nothing to change, but just get used to the fact you might have like 1/2 example, or 3 or 14 examples. That's it. Okay. So the next thing we want to talk about is how to deal with non-bloom features, right? And we know that if your features are categorical and have multiple values, when you select that feature to split on the data set, you're going to have multiple branches, right? Our example here, if you use alloc to split the data set, alloc can take 3 distinct values, meaning that you're going to have 3 branches, right? You split the current data set into 3 subsets, right? But what if your cardinality of your categorical feature is high, right? like 1,000 or even 10,000. That's not uncommon in practice. For example, if your data set like a brand is one of your features, right? You might have 1,000 brands, right? In words like 5,000 brands. That's not uncommon, right? And when I happen to select brand to split on the current data set, I don't want my tree to grow 1,000 branches, right? That kind of violates our belief that the tree should be as small as possible. And how should we deal with that? A common strategy is that, okay, I'm gonna, according to each distinct value that feature can take, we convert it into a binary feature. Take the olive feature as an example, right? Now I'm gonna throw out this olive feature. Instead, I convert this feature into 3 binary features. That is, if olive is summing, if olive is overcast, or if olive is ring. So now we no longer have this categorical feature olive. Instead, we're gonna have 3 more. We're gonna have 3 new binary features. In this way, no matter which particular binary feature is selected, we only grow 2 branches, right? Because it's just binary feature, yes or no. And maybe if the cardinality of the categorical feature is too high, you're gonna create many binary features, right? You don't want to add so many binary features. More concise way is that, okay, I'm gonna group the feature values together, right? So that I can actually reduce the cardinality of the feature. Like, for example, take the brand attribute as an example. You might have 1,000 brands, right? And now I just group them according to the type of product. That might be food brand, that might be sports brand, whatever, right? And then you might reduce the cardinality of this brand feature into 10 groups or 20 groups, right? That largely reduces the cardinality. And then you can either choose use this reduced cardinality, or you further convert them into 10 or 15 binary features. That is really up to you. This is a second common use trick. And then about numerical features, how can we deal with that, right? So this is actually we have already discussed in our previous lecture, right? So you either use thresholds to create a few binary features, or you can bin the numerical features into a categorical feature. Right? So thresholds, it's not necessary to only use one threshold for the numerical feature. Like if you have a height as your feature, right? You can set several thresholds like 3 feet, 5 feet, 8 feet. Right? If height is less than, if it's bigger than 3 feet, it's bigger than 5 feet, it's bigger than 8 feet. Right? You can incorporate as many binary features as you want, as you believe they're going to be useful or meaningful. Or you can just bin them. You can create a few, discretize them into different bins, and then you either get a categorical feature, or you will, if this height was this bin as or not, as a new binary feature. So those are the commonly used strategies to deal with non-boom features. And in practice, you nearly always have to do some kind of pre-processing to convert your raw data into a representation which are easy to deal with. Okay, any questions so far? Okay, it's pretty intuitive, right? Okay, the last thing about decision tree is a very important concept called overfitting. But actually, overfitting is pretty is ubiquitous in machine learning work. So I want to use decision tree to introduce this concept. and then explain why it is harmful, it is not favorable in practice. Right? So, as literally, right, overfitting just means you fit data too well, right? So that sounds kind of a little bit off, right? Because what is machine learning model, right? Machine learning model, we want to train a model to fit the data to be as good as possible, right? And then what does it mean for overfitting? So we see that if your data is good, if your data is perfect, meaning you don't have any extra noises, that's fine. Overfitting is nothing bad. But if your data contains noises, and your model still can overfit it very well, then those noises can take very bad effect, because those noises can mislead the learning procedure, and that with a model which performs badly in the test stage. Okay, so to illustrate overfitting, right, I want to use a concrete example. Right? So we consider running our decision tree to learn a balloon function, okay? And with in general n features where each feature is binary. So you can see that okay, the label is binary, each attribute is binary. Okay? So so you can imagine that the instance space will be finite. Right? Suppose you have n binary attributes. How many instances do you have in total? And dot?
2 to the power n.
Yeah, 2 to the power n, right? Each attribute can take 2 values, right? You have n attributes in total, then you have a total 2 to the power n possible instances, right? That forms the whole instance space. Right? So now let us assume our ground truth balloon function is only determined by the very first feature. This ground truth is also called first fit function. Right? So suppose you have only 2 features. Here we list all possible instances. Right? N equals to 2. We list all possible instances and the labels. Right? You can see that the output is only determined by the first attribute, right? So now, if we feed all the instances with their prior labels to our decision tree, what kind of tree can we learn? Okay. You can try it yourself, but here I just list the tree structure, which is very simple. You're going to select x0 to split on the data set, and then you end up with 2 leaf nodes. Right? This is actually consistent with our ground truth. Right? If x0 is true, then your prediction is true. If your x0 is false, your prediction is false, right? And I mean, again, you can do a very simple exercise to verify the tree. ID3 indeed generates such a tree, right? Actually, here I want to emphasize, no matter what kind of balloon function you have, as long as you provide all the instances, meaning 2 to the power of n instances, with their labels to the decision tree, it can perfectly learn this balloon function. Why?
Because the decision tree is an arbitrary Boolean function, so we'll just become it.
Yeah, you can. Well, you can view it as the representation power, right? You can view the whole path from the root to the leaf node actually represents one particular setting of truth and false of all those features, right? So decision tree is essentially a collection of those rules, right? Well, this is from representation power. From algorithm point of view, you can imagine, okay, every time you just select one attribute, right? And you partition the data, And you will not, at any stage, you will not use up all the current features. Even one particular example, even you end up with a leaf node which contains only one example, you still can get this label. Remember in ID3, the stopping case will be, okay, first all the leaf nodes, all the examples have the same label, or you have used up all the attributes. But however, if you reach the leaf node, however, if you run this decision tree, you will find you will never use up your attributes. Because every example, when you reach, even you partition it into a single instance, right? Only one example inside this subset, you still will not use up your attributes, right? Like if you split, first use x0 split and use x1 split, okay, you end up with this particular example, which is that, right? It won't happen that, okay, when you, at some stage, you have a mixed set of labels, but all the attributes are used up. That won't happen, right? So this is very important. This actually exhibits a very good property of decision tree. That is, it can fit the data as accurate as you want, right? Unless your the prediction is not totally determined by the attributes. If it is totally determined by attributes, okay, when I just select all the attributes x0, x1 to say xn, you will always end up with the particular example and with their labels, right? So that's the power of decision tree, right? So now let's imagine we move to the more general case. You have n binary features, right? And you have all to the power of n examples for training. That means, okay, your training set includes all the instances in the instance space. You have the labels, right? And what will be error on future examples? Zero, right? Because you have already, your training set have already covered all possible instances in instance space, right? And you have actually, the future example has already been seen in the test data. So that means, and we know that decision tree can perfectly fit this data, so it has zero training error. That means the same example you use for test, it always gives the correct prediction. So now it seems the solution seems not that bad, right? And if your data is perfect, the more training data you cover, the better the accuracy you're going to have in the test stage, right? What we have discussed here is kind of extreme case, like you actually have covered all possible instances in the instance space, which of course is not realistic in practice. But here, let's just do some blind experiments and see what will happen, right? When the data is perfect, if you are able to train a data set which includes all possible instances, you have zero training error, you have zero testing, because all the test instances have been seen in the training stage. But now, let us consider what will happen in practice. That is, in practice, our data is inevitably is corrupted by some noises. You cannot expect your data is perfect. Right? So in your data collection, due to all kinds of reasons, you always have kind of like imprecise data or corrupted data. Like imagine you're reading the readouts from the devices, you misread them, or your device has this problematic, it returns the wrong value, all kinds of stuff. It happens all the time. So in practice, there are always more or less some kind of noises injected into the training data. In this case, if your machine learning algorithm, like decision tree, still perfectly fit the training data, that will not sound good, right? Because those noises will bias the learning path, right? Will actually alter the tree structure to make the tree better fit the noises in data, right? That really does not mean good. So to see this more concretely, suppose in our case, we have some corruptions on the outputs on both training test data. Right? say on training data, we have some kind of chance. The label is randomly is a split, right? So it should be false, but now it was split into truth, or it should be truth. It is split into false. And similar things can happen on the test data. Now, even you are able to collect all possible instances in the instance space, right? But the labels in the training set and the labels on the test set will kind of disagree, right? And that means if you're perfectly fit to the training data, you won't perfectly predict the labels in the test set, right? And in this case, I mean, under the noise corruption, what will be the test error? So actually, we can do quite a few experiments, and here are just the results. Right? The x-axis indicates the number of the attributes. Right? We can set a number of attributes n to be 2, 3, 4, 5, and y-axis is just the average test error. And those blue bars represent the average test error. But here we have a standard error bars because we have for each setting we have run experiments many times and just calculate standard deviation to show the stableness of the result. Right? So obviously, the more attributes you have, the more training instances and test instances you have. Right? Remember, the total number of instances is 2 to the power n. Right? So that means your standard deviation is smaller because it is more stable. It is training test on larger data sets. So we can see that the test accuracy or test error, along with the growth of the attribute number, tends to converge to some particular number, which is 0.375. Right? 375. You can see this is a huge gap. Right? If our data is good, right? If our data is not corrupted, right? Training and test error is 0. Right? But now, after a little bit of corruption, oh, by the way, I forgot to tell. Okay, the outputs are randomly corrupted with the probability 0.25. So you see that the test error tends to be 0.375. Right? So we see this is a large gap because after this relatively small chance of corruption, your test error now increases to 37.5%. That's really large, right? So actually, even you don't do these experiments, you just do some mathematical analysis, you will find you can calculate this number. And how can you do that? Right? We can take a look. Right? So, given any example, right? Given any example from the instance space, what is the chance that it can be correctly predicted by our learned tree? There are only two cases. First, if the label of the example in both training and test are not corrupted, they're the same as it should be. Right? And then in the training stage, because our decision tree can perfectly fit every training example, right? In the training stage, it knows the labels here, and in test stage, it uses the same label as prediction. It's the same, right? So this chance will be, we know that the output has a chance 0.25 to be corrupted. So the chance it is not corrupted is 0.75. Right? This is in the training case. And for the test case, it also has 0.75 chance to be uncorrupted. Right? So this part of the probability is just 0.75 times 0.75. And the second case, that is, this particular example is corrupted in both training and test phase. Right? So it was supposed to be true, so now in both training and test stage, it was changed to be false. That's fine because no matter what kind of label it is, the training procedure will guarantee that the decision tree always correctly fit this training example in the test stage, because the test label and the training label is the same, right? So it still gives the correct prediction or consistent prediction. prediction. And what is chance for this case? We know that this example at the training stage has a chance 0.25 to be corrected, right? At test stage has another 0.25 chance to be corrected. So you multiply them together, you get the probability of a second case, right? And then summarize them together, we know that for any example, the probability it will be correctly predicted will be 0.625, just add them together, right? And you just subtract 1 by this 0.625, you know the chance of incorrect prediction, which is 0.375. And of course, you can analyze in another direction and consider cases when you're going to make a wrong prediction, which I'm going to leave you reading the remaining part, but it's pretty similar. Any questions so far?
How do you know that the training examples are consistent versus 5%?
Oh, that's a good question. This is just some minor experiments. We actually assume that, okay, the training data and test data, their labels have a 0.25 chance to be corrected. But in practice, we rarely know that. This is just one example to show or to analyze what the consequence the overfitting will be. Any other question regarding those analysis? So this is a very simple and ideal case, right? So first, in practice, we'll never be able to collect the entire instance space, right? And secondly, we actually do not know in practice what is the chance the labels of training or test data are corrected. But here, just putting all those ideal situations together, right? Through this analysis, you can see that the effect of the overfitting, right? When the data contains some noises and your learning procedure is sensitive to those noises, it kind of change the right direction, right? And give you a bad generalization performance on the future examples. So, okay, we know that training accuracy, no matter what kind of noises you have, is still 100% accurate. This is probably a distinct treatment. So why is the classifier not perfect? Because the classifier overfits the training data. Like, no matter what kind of noises are injected in the training data, the classifier will do its best to fit the data, including those noises. And those noises actually mislead the classifier and lead to degraded performance in the test stage. That's why we do not favor overfitting, because in practice we cannot prevent noises. We always have imperfect data in practice. So if your learning model is too strong, is too flexible, it fits the noises so well, and usually it will decrease the generalization performance. Okay. So here is a summary of the overfitting. Right? So the learning algorithm, why we do not favor overfitting, because the learning algorithm fits noise in the data, and if your training accuracy is 100% or zero training error, in other words, that's a bad sign. Actually, you have to come out a way to regularize your learning procedure, your classifier, to make it not fit the training data so well. Okay, now let us look at some observations in the practical application. The previous example we discussed is kind of like mind experiment in a very limited and ideal case, right? And now we show the results by running decision trees on real-world data. So this figure was still from Tom Michel's classical book in machine learning. Okay? So the x-axis size of tree. So you can see the size of tree is measured in terms of number of nodes. The more the nodes you have, the larger the tree. Maybe it's wider or deeper, right? And x-axis indicates the accuracy. And then we have two types of accuracies. And the the solid line indicates the training accuracy, meaning that, okay, I use the current tree to predict examples on a training set what is accuracy, right? And the dashed line indicates test accuracy, meaning that I have a separate test set, right? Every time at the current stage, I just use my learned tree to predict the examples on test set and what is the test accuracy. So from these two curves, what we can observe is that, okay, at the beginning, when the tree is very small, right, when you increase the tree, you can see that both the training and test accuracy increase, right? Meaning that, okay, feeding the training data better and better can indeed help you predict examples in the future, right? But at some stage, right, we see that when the size of tree grows to some degree, right, and when you keep growing the tree, right, you can continue to increase the training accuracy, but test accuracy starts to decrease. This is the point where you kind of like overfit the data. And when you keep growing the tree, right, and keeps growing the tree, you see that, okay, you're fitting the tree data better and better, right? It keeps increasing, right? At the same time, you can see your test accuracy is gradually decreasing. So in practice, we always find a good starting point, right, where we find, okay, we get best test accuracy, right, here, because machine learning cares about the generalization performance, right, not only on the training accuracy. Okay, so now we have learned the concept of overfitting. We know that it is not favorable in practice because of noise, right? And decision tree is a kind of a classifier or predictor which tends to overfit data, right? Obviously, we don't want to happen. Right? That means in practice we need to control the growth of the tree to avoid it perfectly fits the data. Right? How can we do that? There are several strategies. So first, a very straightforward strategy. I'm going to fix the depth of the tree. Right? I do not want it to grow to 100 levels. Right? I require the tree to stop growing at say level 10. Right? And it's very easy to implement. Right? I just set a maximum tree depth, and when the tree grows to depth 10, no matter if the examples are shared the same label or not, just stop growing. And create a leaf node and use the most common label in the current set as the leaf nodes label. And there are some extreme cases. If you just grow one level, such a tree is called decision stump. And of course, if you set up a maximum level to be 1, that's just too extreme. That won't work well in practice. That's kind of underfit data, right? But we'll see that when we talk about the ensemble learning. And decision tree, a decision stump can serve as a very good base learner, and we can combine many weak learners like decision stumps together, and then to assemble a very strong classifier. A second approach is that I'm going to dynamically determine if I will keep growing or stop here. Right? So how can we do that? I split the training data. I find a separate set which we call held-out set. Right? And then I run my decision tree learning on the remaining training set. Right? And then every time before I'm going to grow the tree, I just test the performance on held-out set. And then when I grow the branches and add a few new nodes, then I test the performance on the held set again. If the performance drops, that meaning, okay, I cannot grow. Meaning that because I grow those new branches, nodes, it leads to the degradation of performance. I'm gonna stop. So this can be tested throughout the whole tree construction procedure. So you end up with a tree structure might be kind of weird. Like maybe at some intermediate nodes, it does not allow you to grow, but at some left branch, it might allow you to grow quite a few levels because this is dynamic. Right? It's dynamic during the tree construction procedure. And the third strategy is to do the post-pruning. Right? So we can first grow the tree without caring about the size. Right? I grow it as large as possible, and then I determine to and then I do a separate stage to prune the tree. Like I can either use a validation set, which is just like held-out set, and to prune from bottom to top in a greedy way, or we convert the tree into a set of rules. Right? You mentioned that a prediction rule essentially passes from the root to the leaf, right? And I use whatever data set or heuristics to determine to prune those rules, and then combine those rules together to form our prune tree. So those are the strategies of the pruning and control the growth. And most common use will be the second strategy and the first strategy. Okay, any questions so far? Great. So now we have finished up the decision trees. So to summarize, decision trees are a popular machine learning tool, very classical, very popular, in that the prediction is very easy, it's very expressive. Remember the decision boundaries we have drawn before. It can be highly nonlinear. It's not a simple linear model, and it's very interpretable. Right? We know for each test how our decision can be made. Like this whole rule we can trace. Right? We can trace the whole rule, and then we can debug the tree. Right? And the learning algorithm essentially is a greedy heuristic to find a tree to be as small as possible, but it cannot guarantee to find the truly smallest tree. And it also can be used for regression. If you stop at some leaf node, and you just take the average of the continuous labels or the medium continuous label as your label, you can do the regression. And finally, it's also very important, decision trees are prone to overfitting. So in practice, you always need to take some kind of action to prevent overfitting. Okay, so again, let me just encourage you to do homework one as soon as possible. You will see that I'm happy to see some question raised in cameras last night talking about homework one. Right? So I hope anyone who hasn't started yet has started to do that. You cannot expect finish it like in 1 day or 3 hours, because there are many questions, and it will require you first to do some manual construction of those trees, and that will guarantee you to totally understand the whole procedure. And then you implement this tree learning algorithm and test them on the data set. And trust me, you're gonna need some time to debug. So please start the homework one as soon as possible. Okay. Before we talk about the next learning algorithm, I want to look at a little bit theory. Don't be scared. We won't go very in depth about computational learning theory, but we do need, because this is a tutorial course, right? We do need to learn some basic concepts, which are used throughout all kinds of machine learning models, and the ideas which can help us to understand the motivation of the important algorithm like small vector machines, and explain or justify the phenomenon common phenomenon in machine learning practice, like the trade-off the randomizer and the training data loss. So, okay, we're gonna first talk about the general framework and key concepts in computational learning theory, which includes Imperial Error, Generalization Rule, and the learning goal. What have a good learner. You see that a little bit from our intuition, because we actually don't have any deterministic guarantees about learning algorithms. All our guarantees can only be stated in terms of kind of probability. I will explain why later. Then we'll introduce this key concept called path learnability. So path learnability can be viewed as a criterion to differentiate those efficient learners or inefficient learners. If you say, okay, some type of target functions can be path learnable by some learning algorithm, meaning that learning algorithm is really efficient and can be practically useful. And then we'll make some kind of formal connection to the principle of Occam's razor. We'll use a very simplified and ideal case to justify the Occam's razor principle. Okay? So here's the checkpoint, right? Before we proceed, let us look at the big picture we have seen so far, right? So we have introduced the supervised learning framework. We know that in the supervised learning, we have some instance space, we have label space, we have a target function which labels the instances, right? And we have a hypothesis space, right? Hypothesis space is essentially the family of the functions candidates our learning algorithm is going to search over, right? And then, given the labeled training set, our learning algorithm will search over the hypothesis space and find the best one, right? And we believe this H is close to the branches, right? And in the prediction, we just use our learned hypothesis to make predictions, right? And there are many specific learners. We mentioned that before, right? And we have gone through the very first one, decision trees, and also we have learned an important concept that's called overheating, right? So this is a bigger picture, right? So what is standing for computational learning field? On the computational learning field, we always assume, okay, we have a machine learning model. We have a fixed training set based on which we can train our model. And we're going to deploy our model in while, meaning that, okay, I can collect whatever I'm saying, future examples to test. Right? And then the key question that the computational learning theory wants to answer is that how well will your learned model perform on future instances? Right? So now let us introduce a few locations, right? In a supervised learning setup when we try to formulate this question, right? So first, in supervised learning, we have instance space X, right? And we introduce concept space C to denote the type or the family of target functions. So we can view this concept space as the type of the target function. Suppose your target function is just 3 order polynomials, then your concept space might be all the polynomials. Right? And suppose your target function is a linear function, and it's a particular linear function, right? And then your concept space will be the collection of all the linear functions. It just indicates the type of the target function. And in the training procedure, we also need to define a hypothesis space, H, which is another set of functions. The hypothesis space essentially defines the search range. And the biggest difference is that in practice, we often do not know the exact concept space, or we'll have to assume a very large concept space. Suppose you want to predict the stock price. Right? Do you know what type of the target function is it? Is it polynomial? Is it exponential function? Is it sine cosine function? You don't know, right? It's very difficult to know. you don't know the detailed type, or you have to assume very, very large type, right? You can assume, okay, it is a continuous function. Or it is a function whose output is between 0 to 1,000 or 10,000, whatever, right? But for hypothesis space, it must be very clear during the training procedure. Otherwise, you cannot run a learning algorithm. You must specify the hypothesis space to be, say, sine functions, cosine functions, or quadratic functions, whatever. So actually, the detailed learning algorithm has already specified the hypothesis space. So don't confuse about the two spaces. So, and then we have a training instances, which are a list of pairs, right? Pairs of instances from instance space and the labels provided by the target function. And what we want is that, okay, I want to apply a hypothesis from a hypothesis space such that the prediction made by the hypothesis is the same as the prediction made by the branches. There are two possible cases. First, for all the training instances, I want my prediction made by the hypothesis the same as the prediction made by the branches, right? That means I want my training. I want my learned hypothesis to fit the training data well. And there is another case which is more general. For all possible cases, for all possible instances in instance space, I want the prediction of my learned hypothesis is consistent with the branches. So obviously, you want this to happen. You want this to happen. So, in practice, we're going to evaluate our learned hypothesis on some other examples. And those examples are drawn according to some data distribution. So here, we assume our training instances and test instances are generated from some data distribution B. And this data distribution is really unknown and very difficult to know. Like you can imagine if your task is to classify images, right? So what are you going to do to collect the training and test set? It's just a search on the web, right? For example, Google image and just randomly collect a bunch of images and their labels, right? But who produced those images? It might come from some photographer, or it might come from some people who take a picture with your iPhone, right? With their iPhones. So the whole procedure to generate those instances are quite complicated, and it's really very difficult to know that. So for mathematical convenience, just assume that okay, they're gonna be generated by some unknown, highly complicated distribution B, right? And both training and test. But this is just a theoretical thing, right? Because we see that actually we do not want to make any assumption about this data distribution. Just tell you, okay, they are sampled from some kind of complicated mechanism, and we don't know that. Any questions so far? Okay, I feel everyone is comfortable. It's just some bunch of settings before this, which is necessary before we talk about theory. Okay. So now, what is the gold standard to measure the performance, the generalization of your learned hypothesis? Right? So the gold standard measure is defined as the generalization error. Right? So what is the generalization error? So given this unknown distribution D over the instances, right? So the error of a follows for x were sampled from this data distribution D. And then x can be arbitrary, but it just follows the distribution D. And what is the chance your prediction made by H is different from the ground truth prediction? So you can see from this distribution D, it actually includes all possible cases of x. Right? That is called the generalization error. And of course, our goal is to make this generalization error to be as small as possible. Right? Okay, here I want to give a more intuitive explanation of this definition, right? So suppose this is our instance space, X, right? So remember, we assume some data distribution D, meaning that, okay, we have some distribution on X, right? This might be some high density regions, meaning the points here are more likely to be generated than the points here. Right? So now, this is the word, this rule circle covers all the points where the ground truth function f labels as positive. And then suppose you have learned a target function h, which labels another portion of the instances as positive. Right? So you can see that the two blue circles overlap largely, but not completely overlap, right? There is some disagreement. And the generalization error comes from the area of the disagreement. And essentially, the generalization error is actually the probability of those disagreement area under the data distribution, right? So these two areas where is the place, is the region where your prediction is inconsistent with the ground truth, right? And we need to consider the distribution. So the generalization error is actually the probability mass of these two disagreement areas. Okay. Any questions so far? Hopefully this is kind of intuitive for everyone. Great. So in addition to the generalization error, we have another commonly used error, which is called imperial error. So what is imperial error? It is just the training error. That's it. So I won't read through this long definition, but it just means training error. So if you use if you have learned about this H, right? And then you just use H to predict the labels of the training data, and adjust the calculus error. This is called imperial error. So we denote the imperial error by error S, because S is the training set, right? And we denote the generalization error by error D, because D indicates the data distribution, right? So with the definition of imperial error and the generalization error, we can define overfitting in a more formal way. That is, your model is viewed as overfit the training data if the imperial error on the training set is substantially lower than the generalization error. So your imperial error is almost 0, but the generalization error is 70%. Right? That really indicates your model overfits the training data too much, and it also perfectly fits the noise in the training data. Okay. So now let me release those notations. So we use X to indicate instances space, Y indicates output space. We denote the unknown data distribution over the instance space by D, right? We denote by F the unknown target function, right? And F is the instance from the concept class C, right? Concept class is actually the type of the target function. And H, small h, is the hypothesis, right? Which is also matching from instance space error passage to indicate empirical error or the training error on the error of the training set. So here are a few critical questions that computational learning theory wants to answer. So first, although the generalization error or true error seems very good, right, perfectly, but we'll never be able to compute the true error. Why?
You don't know the F.
What?
You don't know the F. You don't know the actual like gold standard generally.
Yeah. You actually don't know the data distribution. As we just mentioned, right? You don't have you have no idea about the mechanism who generates the data, the instances, right? So like when you collect images for image classification, you can search on the web and download them, right? But you never know what kind of mechanism which generates this, right? What is the probability to generate dog? What's the probability to generate a flower, right? You don't know that, right? Without knowing the underlying distribution of the instances, you'll never be able to exactly calculate its probability, right? Not to mention, you don't know f either. You don't know the target function either. But it is always easy to compute the empirical error, right? Because you have collected the training set, right? After your training, you just test on the training set. You get the training error. So, naturally, one want to ask, right? Given the training error or the empirical error is so easy to get, right? Can we use empirical error to describe or bound the true error? Can we claim that, okay, although I don't know exact true error, can I say, okay, I believe the true error is upper bounded by some expression in terms of the empirical error? And then by just looking at bound, I can estimate, okay, how large this true error will be, right? And then later we'll see several such kind of bounds. And actually, the classical fallback machines is also motivated by such a bound. It's called the generalization error bound. And second, for different types of target functions, are they learnable? So what does it mean for learnable? Right? We should first define that, which we're going to discuss later. And also, how many examples for a particular learning algorithm? How many examples to achieve certain performance? Right? How many examples at least do we need? This is called sample complexity. Obviously, we want number of examples to be as small as possible. And finally, how much cost does an algorithm take to learn a type of target function? This is regarding computational complexity. I think it is familiar with everyone, right? Everyone is familiar with that. So, to answer all those questions, right, we need to first define what is the good learning. What is the good learning result? This is actually very important. So, to make the theory useful, not just theory, first, we cannot expect a learning algorithm can exactly learn a target function. The reason is that first, the data set, the training data is limited. And the training instance, the instance space is usually infinite, right? So although we have used some simple example, like Bloom function, you know the instance space is finite, right? But in most practical applications, you see that the instance space is nearly always infinite. You can only collect a finite number of the instances. And depends a lot, right? those training sets usually are not representative for the whole space. That means even for the same training data, there can be multiple functions which can equally well fit the training data. So obviously, we don't assume we have multiple target functions, right? Or have one target function. So we cannot expect you can find precisely the target function. And secondly, because you don't know the data distribution. Right? So when you train examples, suppose your training collection is just follow the data distribution. What you collect are just those high likely examples. Right? In other words, you can imagine that if you sample data from some kind of distribution, most likely you're gonna sample them from high density regions. Right? And the low density, the low chance, the low density region, the examples in low density regions are much unlikely to be collected. So you fit the trained data. That means you fit well in predicting those examples coming from high density regions. Then that means it is likely that there are some rare examples which never appeared before. You're gonna make predictions. You're gonna make mistakes. Right? So due to these two reasons, first, your training data is always finite. Secondly, you don't know data distribution. We're gonna never expect our learning algorithm can exactly capture the target function. And someone asked, can we expect that our learner guaranteed to find a good approximation to the target function? The answer is no as well. So it's kind of pessimistic, but this is the truth, right? So why? Because the quality of your learned function or hypothesis is also dependent on data quality, right? So remember, your data is collected from some unknown distribution, right? The data is essentially a random variable. In one training, right? In one training process, you might have collected the data of good quality. It's kind of like cover all the instance space in a good way, and then you can expect your learned hypothesis is a good approximation. Right? But what if you have collected a set of data which only covers a small range of the instance space? Right? In that case, your learned hypothesis is very likely to be bad, right? To be quite different from the target function. So it actually depends on the quality of the data set. And given all those analysis, right, practical constraints, then how would we expect a good learner or good learning model is? Right? So we need to put some probability statement. So we see that if we have a good learner, in real applications, right, is that this good learner will have a high probability learn a close approximation to the target concept. That's how, in computational learning theory, people define a good learner. We need to put some probability statement. Remember, because the learned hypothesis dependent on data, and data itself is random. But if we can guarantee some good learner always some high chance to learn a good approximation to target concept, we will hope this learner is really good. Okay. So now, based on this, our phase, right, our realistic expectation of good learner, we're going to introduce the concept of probability, probably approximate correctness, abbreviated as a pack learning. So as we just mentioned, pack learning a path learnability can be viewed as a criterion to differentiate efficient good learners and other learners. So, of course, to be aligned with our belief or expectation of good learners, we have to introduce a few notations. First, we're going to introduce epsilon and delta, which indicates the level of this probability and the level of this approximation. And with epsilon delta, we can formally state our expectation of a good learner as like that. So please bear with this a little bit long sentence, but I think the meaning is clear. So with probability at least 1 minus delta, a learner produces a hypothesis with error by most epsilon. So you can see that, let me use a concrete example. Suppose delta is 0.1, right? Epsilon is 0.1 as well, right? I say that, okay, with probability at least 0.9, you find a hypothesis with error at most 0.1. Of course, the smaller epsilon, the smaller delta, the better the learned hypothesis, the better the learner. Right? So now, what is path learnability? Right? Path learnability just says that, okay, whether if a given learning algorithm can learn a type of target functions in a very sample efficient way. So what's the definition? Right? Definition is here. So the concept of C, so you can view it as the type of the target function C, is path learnable by our learning algorithm L, of course using a hypothesis space H. If for every possible target function in this type, right, for every possible data distribution over the instance space, and for any fixed epsilon and delta level, L only uses a polynomial number of training examples to its 4 numbers. It can have a chance at least 1 minus delta to find a hypothesis whose error at most epsilon. So you can see that it says that, okay, first L can learn a good hypothesis from hypothesis space H, right? And but it doesn't need too many training examples. The number of training examples is only determined by these 4 numbers: 1 over epsilon, 1 over delta, and here is the dimension of the attributes, the number of attributes, and the size of hypothesis space. I only need a polynomial to these 4 numbers. Sample example is polynomial to these 4 numbers. Then I can guarantee you, with the chance at least 1 minus delta, I can find a good hypothesis whose true error at most epsilon. That's the definition of path learnability, right? So again, epsilon here indicates the generalization error. Delta here indicates the confidence level. So any questions so far regarding the understanding of this concept, this definition? Yeah, it's kind of tedious. If you feel uncomfortable with that, I'm sorry they give such a lengthy definition, but to make it clear, you have to put this long sentence. But the basic idea is that, okay, L is good enough, is efficient enough. When is L is good enough, efficient enough? Right? I don't need too many examples. I only need a polynomial number of examples in terms of some parameters, and then I can have a high chance to learn a good approximation of the target function. That's it. I would suggest you, if you still feel uncomfortable and not get used to that, read through these sentences 3 times or 4 times, you will get used to that. So, and further, if we want to make some requirement on the computational cost, we can further define the computational cost is also, or the time complexity is also polynomial in 1 over epsilon, 1 over delta, number of attributes, practical abilities to identify if those learners are really good learners, are practically useful because you don't need to collect an exponential number of the training examples to the specific generalization error level and confidence level, right? So first, we require polynomial sample complexity, meaning that I want the learner can effectively leverage sample information to find hypotheses. I don't need many examples. I don't need a huge number of training examples because in practice, training data collection is also costly. Secondly, if we want the algorithm can efficiently type learn the type of target function, then we want the polynomial time complexity. So if you're from computer science, you should know that polynomial time complexity is kind of like a criterion which we believe your algorithm is practically useful, right? You don't want your time complexity to grow exponentially to the problem skew, right? And also, type learnability is kind of a strong requirement because remember, it must satisfy for every possible app, every possible distribution, at every possible level of epsilon delta. That means that for any given error or arbitrary small error, for every target function f, we can always find a hypothesis h whose true error is less than this level, right? So that make many theory or lemmas assume, okay, your hypothesis space is large enough such that it contains the concept class C. Right? So in this case, we call C is probably type learnable by L. And also, this is a worst case definition. Right? And if you claim that your algorithm can type learn some type of target functions, then you must meet the accuracy level or error level and the confidence level for every data distribution. So it's this distribution of free assumption, and for every target function in the concept class for this type of target functions. Okay, any questions so far? Looks everyone is comfortable with this. Okay, I'm really happy because those are quite attractive, to my experience, quite attractive headache for many